Floppy disks are obsolete, but in my opinion it is still interesting piece of technology. Let's explain how it works, how data is stored in floppy disk, how floppy drive retrieve data from floppy disk, and how data is structured and encoded based on 3.5-inch high-density floppy disk and my Arduino floppy disk controller. The floppy disk. Floppy disk is a storage medium that could handle up to 1,440 kilobytes of data. It uses magnetic fields to store digital data. Plastic housing have shutter that protects disk surface from dust and mechanical damage. Movable tab that allows write protection to be on and off. Inside plastic housing, there is plastic disc coated with cobalt-doped iron oxide material. This magnetic material allows to store digital data in FORM of magnetic domains. Polyester sheet that reduce friction while disk is spinning and clean disk from dust. A hub is attached to disk that allows motor to engage and spin the disk. The disk is divided into two sides numbered 0 and 1. Each side contain 80 circular tracks numbered from 0 to 79. Each track contain 18 sectors numbered from 1 to 18. Sectors are not stored physically on track. Track is written as continuous signal, and sectors appear as logical division of track content. Data in tracks is stored using modified frequency modulation at frequency around 500 kHz. MFM encoding uses 3 pulse lengths to encode MFM bits. Short pulse produce 10 MFM bits. Medium pulse produce 100. Long pulse produce 1000. 2 MFM bits encode single byte bit. 10 and 00 encodes 0. 01 encodes 1. 11 is invalid and should never occur. Here is an example of MFM decoding. Start from measuring pulse lengths. Then translate it to MFM bits, then divide MFM bits into pairs, then decode pairs to byte bits, and form a byte from bits. Each track begins with track start header. Bunch of 4E sync bytes, bunch of 00 sync bytes, and signature C2 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 FC. Next there is sectors. Each sector is constructed from header and data. Sector header first. Bunch of 4E sync bytes, bunch of 00 sync bytes, then there is signature A1 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 FE, then 4 bytes sector header, and on end 2 bytes cyclic redundancy check calculated from signature and header. Sector header contain 1 byte track number, 1 byte head number, 1 byte sector number, 1 byte sector size, upper bits of 16-bit number. Then sector data. Bunch of 4E sync bytes. Bunch of 00 sync bytes. Then signature A1 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 FB. Then 512 sector data bytes. This is actual data that is written into RAM on floppy read, on end 2 bytes CRC, calculated from signature and data. And after last sector, there is gap and whole track repeats since it is written to circle. Full disk image is created by sectors data that is ordered named logical block addressing. Start from track 0 side 0, data from sectors 1 to 18, then track 0 side 1, data from sectors 1 to 18, then track 1 side 0, data from sectors 1 to 18, then track 1 side 1, data from sectors 1 to 18, and so on, up to track 79. Floppy disk drive. Floppy disk drive is a device that allows read and write data from and to floppy disk. On front there is a slot with flap to insert floppy disk, button to eject inserted disk, and small LED to indicate that drive is in use. On the back, floppy disk drive is interfaced using 34-pin header. A power +5 and +12 volts are delivered via this plug. There is also stepper motor exposed. Inside drive from top there is movable head holder. It contains 2 heads, which is simply a pair or tiny coils to read and write signal. A stepper motor with long screw attached to heads holder allows moving heads in tiny steps to switch heads from track to track. Lastly, there is mechanism supports inserting and ejecting disk. Inside drive from bottom, there is circuit board with brushless synchronous motor that actually spin disks at around 360 revolutions per minute. On circuit board, there is main IC that handles communication via interface port, amplifies signal from heads and convert it into pulses, controls stepper motor, Control motor driver IC, reads sensor state, for example index or write protection. Stepper motor allows to move heads beyond track 79. Some floppy disks have tach number 80, which is possible to read it manually, as a simple copy protection mechanism. Write protection is done by simple switch, which detects tab's position in floppy disk. Based on that write is allowed or not. 34-pin header interface pinouts. Odd pins, 1 through 33 are ground. Pin 2 density, select, 0 volts, high density, 5 volts, low density. Pin 4 and 6 are not used. Pin 8, 5 volts to 0 volts transition indicate start of track. Pin 10, enable motor, 0 volts, spins the motor. Pin 12 not used by drive. Pin 14, drive enable, 0 volts means enabled, LED is on. Pin 16 not used by drive. Pin 18, stepper motor, step direction, 0 volts, towards track 79, 5 volts, towards track 0. Pin 20, step, each signal transition, moves head by 1 step, in direction set by DIR pin. Pin 22, write data pulses. Pin 24, write enable. Pin 26, track 0 indicator, 0 volts, heads is above track 0. Pin 28, write protect, 0 volts, disk protected. Pin 30, read data pulses. Pin 32, head/side select. Pin 34, disk change, 0 volts, indicate ready to work, 5 volts, disk change. Floppy drive flex cable have twist, which redirects pin 16 to pin 10 and pin 14 to pin 12. This makes possible for disk controller to control 2 drives on single cable without any kind of jumpers. Lastly, floppy disk drive does not perform any logic or decoding on read/written data. It is simple analog device. It is up to floppy disk controller to interpret or create pulses. Disk image. The capacity of floppy disk is 1440 kilobytes, but not all of its capacity can be used to store files. Some overhead are added to keep information about disk and file system. First 512 bytes of image, a boot sector aka track 0 side 0 sector 1, contain necessary information for BIOS and operating system, characterizing disk type, capability, and content. It contain information about file system type and boot code. This floppy disk that I ripped was formatted using file allocation table aka FAT file system, mostly used on PC, and here is structure of partition boot sector. Start with 3 bytes jump instruction for boot time, it jumps to address at offset 3e hex. 8 bytes OEM name in ASCII. 25 bytes BIOS parameter block, 26 bytes extended BIOS parameter block, 448 bytes bootstrap code, 2 bytes end of sector marker 55AA in hex. BIOS parameter block. 2 byte number of bytes per sector. 1 byte number of sectors in cluster. 2 byte number of sectors of this partition boot sector. 1 byte number of copies of file allocation table. 2 byte number of entries that can be stored in root directory. 2 byte number of sectors in volume if its number fits in 16-bit number, otherwise extended field is used. 1 byte media type, F0 means floppy disk. 2 byte number of sectors per file allocation table. 2 byte number of sectors per track. 2 byte number of heads in drive. 4 byte number of hidden sectors. 4 byte number of sectors per volume if it cannot fit into previous 16-bit number. Extended BIOS parameter block. 1 byte physical disk number for floppies, it is 00 hex. 1 byte unused. 1 byte signature 28 hex or 29 hex. 4 byte volume serial number. 11 bytes volume label name in ASCII. 8 bytes file system ID. Boot sector code is in Windows 98 boot floppy disk. It loads io.sys and ms-dos.sys files from floppy to memory. io.sys is a DOS kernel, while ms-dos.sys is a text config file. After loading boot code, jumps to executing io.sys DOS kernel. After partition boot sector, there is actual file allocation table, which is 9 sectors long and its copy just next to it, second 9 sectors. File allocation table is a table of sector state. Sector can be occupied by file or can be empty. Each entry of FAT is 12 bits long, so 3 bytes form a 2 table entries. If sector contain file, table value point to next sector of the file, or end of file marker. After 2 file allocation tables, main FAT and its safety copy, there is root directory entry. It contain a list of files and directories in the file system. A root directory entry contain 8 bytes ASCII file name, 3 bytes ASCII file extension, 1 byte file attribute, 1 byte size of characters in file name and extension, 1 byte time of creation in milliseconds, 2 bytes time of creation, 2 bytes date of creation, 2 bytes time of last access, 2 bytes reserved, 2 bytes time of creation or last modification of file, 2 bytes date of creation or last modification of file, 2 bytes number of first cluster along with FAT table index of next file sector. 4 bytes file size. To get file content, operation system first must read corresponding directory entry. Read file size and file's first cluster. Cluster number can be converted to physical sector using this equation. After reading first file sector, then OS need to access FAT at index of current cluster to get number of next cluster, which again needs to be converted to physical sector using an equation. In FAT12, sector can be occupied only by single file. In case when sector is not fully filled with file content, second file content cannot be stored in same sector. So actual storage capacity is smaller and depends also on number of files in file system. Floppy disk controller. For the purpose of this video, I have created this simple Arduino-based floppy disk controller. It implements read from floppy disk. Atmega 328P is connected to floppy disk using flex cable, and to PC using USB, aka serial port. Almost all signals are directly connected to Arduino, except read signal pulses. It is connected to D flip-flop, which switch output state on each rising edge of read signal pulses. This simplifies read procedure since microcontroller can measure pulse length on each D flip-flop output state change. Because read pulses are at around 500 kHz frequency, Arduino does not have much time from pulse to pulse, so some optimization must be implemented to not miss any pulse. My implementation are able to read time from pulse to pulse, and quantize it to 3 states, long, medium, short, and store that value in buffer. When buffer are full, then micro CPU stops reading pulses and send timing to PC via serial port. Buffer size, create from almost all static RAM of Atmega 328P is enough to store pulses of whole sector header and data with sync pulses and signature, plus sync pulses of next sector. But not to store full track. To read full track, sectors needs to be read one by one, by introducing some delay after start of track signal, which slows down read process a little bit. All pulses processing is done in PC in Python script, which control floppy disk using Arduino pinouts, decode MFM, calculate CRC, and compare with CRC read from floppy disk. If CRC match, then that sector can be saved in bin file, otherwise controller move head back and forward and try read sector again. Slowly, all sectors in logical block addressing order is ripped from disk to bin file. As you can see, ripped disk image is all but to be mounted and view its content. It is also able to boot using VirtualBox. This is end. Thanks for watching.